Okay, what's our explanation for the common ion effect?
Isn't it it comes without electrons,
Oh. You can add an ion to make something solid. I didn't hear you.
I said adding a specific ion to solution.
Okay. Or shift equilibrium could include solidify. So if I've got X and Y, and X and Y go into the water, and I've got X and I've got Y. I could put in Z, Y, and have some Z's and some more Y's, and cause something to happen up here because I added more Y's to this. Does that graphically make sense? No? Okay. How about...
is it kind of like the forcing?
Yeah, sure. Let's say I've got... Let's say for some reason I needed to get the chlorides out. Is there something I could do with that? Okay. Well, this is a sort of a little equilibrium here, right? We okay with that? It looks more like that though, right? It's, for all practical purposes, all the sodium is dissociated. But let's say that I wanted the sodium chloride to solidify. Is there something I could do to make the sodium chloride solidify? Let's say that I put in sodium nitrate, also soluble. So now the amount of Na went up. Are we okay with that? Me saying the amount of Na just went up? I just increased the amount of sodium in the solution. So what's going to happen? It's going to shift back this direction, and I'll actually get more solid sodium chloride there.
Okay, so going back to your question a little bit.
Okay.
If our X and Z have to be different, or they
They have to be different.
Okay.
All I'm trying to do is have one of the things that is in common.
Can you use the common ion effect and not like make something liquid again, or like not necessarily make something solid?
Can you use the common ion effect? We open the door for you. You got to go around now.
Can't give the long door. I didn't see anyone in here.
Oh, no, there was no one in here.
Like 8 minutes ago.
In the office on Moodle trying to
All right.
answer.
I just got stopped upstairs by usual suspects asking questions. Swapped vehicles for the day. Yeah, it was all against you. Wait, what did you just ask me, Kay?
If you could like use the common ion effect but not make something into a solid.
You mean make it stay aqueous?
Yeah, like not necessarily like have your end goal be to make something a solid again. Get it out.
I can't think of an instance because as I add more species to it, the stuff is more likely to solidify, not more likely to become aqueous because the water molecules become consumed with doing their job of being aqueous, and at some point they're going to run out of water molecules and the solution is going to be saturated. So I can't think of an instant where I can take something that's a solid and use common ion effect to swap it over because the thing isn't an ion. Solid isn't there are no ions associated with the solid per se that are available to be messed around with, I guess. Yeah.
So is forcing the solid state part of the definition of the common ion?
No, it's just it's a option. No, would adding water do that? Well, it's not a common ion, first off, so it doesn't apply to this, but would adding water do what? Shift an equilibrium?
This is what she was asking me. So,
Sure, but it's not a common ion. Explain how to remove an ion from water there that you don't want to drink. So you could use this, right? Common ion effect. So if I've got barium, I don't know, barium sitting in the water, what could I do to get rid of it? Add some sulfate. So I could put in some sulfuric acid. When I do that, I'm going to end up with some barium sulfate here. And now all the if I put enough of the sulfuric acid in, then this here is a solid, and all the barium that's an ion, that's an aqueous form, is going to be removed and turn into a solid. Yeah.
is that common ion on there? Or is that something?
No, it could be the common. No, it's not. Let me erase this. In the instance I gave you, it wouldn't be common ion effect. For a common ion effect to work with this, you could do something like, let's say in the solution I had barium nitrate. Maybe nitrate's a bad example, but whatever. Let's do barium chloride. Nitrate's too soluble. So I've got barium chloride, and these guys are aqueous. If I added to this some NaCl to here, I will have increased the amount of chloride and then caused this to become barium chloride, the solid. So there's common ion effect. What?
No, you're missing it. Okay, so can we go back up to the top really quick? So in that instance, why is sodium?
That's not a question. Why is sodium?
No. The y in your equation,
No.
right there,
Oh.
transfers into sodium.
Sure.
Okay.
She's just saying, my example, the common ion effect on the left was Y. And on the right, the common ion effect is sodium. So in that instance, yes. I know. It doesn't matter. She's saying, I am saying in that first thing that I wrote up there, that in that particular instance, Y is acting as the common ion, okay? And then in my example of real stuff, the common ion is sodium.
And the second one will come back. Chloride.
And the second one, the common ion, is chloride.
Thank you.
What's wrong, Ben?
I just don't even know what common ion is.
I've got two substances, sodium chloride and sodium nitrate. There's a common ion between them, right? So I can put sodium nitrate in and have sodium chloride do something because I added a common ion to it. Okay. So, we okay? Not okay? These should definitely be the first two questions on the exam. What, yo,
Oh, so on the exam, would we have to like give an example of the common ion effect?
I haven't written it, so maybe I'll think about that question. Which is of the following dissolves the most in water? So, to answer this question, what do you need? You need to know what the KSPs are. So, which one of these has the largest, albeit small, KSP? What's the calcium sulfates?
KSP or?
Yeah. Well, wait, what else would you tell me?
Like
What? Concentration and KSP are related to each other, but they're absolutely not the same thing. So I would have to look up each of these KSPs. Does somebody actually do that? Or are you going to make me do it? Well, So we've got 4 KSPs. This one is ridiculous. This is a 10 to the negative 38. This one is also pretty ridiculous. This is a 10 to the negative 28. The sulfate one, this is a 10 to the negative 5th. And then the zinc is 10 to the negative 7th.
So you only care about.
If I gave you $150 million, do you care about the 50 part? Or would you care if I only gave you $150? What's more important? The fact that I said million, right? As opposed to just saying 100. So when would the decimal part in front of the exponent be important? If the exponents are the same, right? If I'm talking about 2 10 to the negative 7ths, then I need to look at the decimal. But otherwise, the difference between 10 to the negative 6 and 10 to the negative 5th is going to be 10. So even if the numbers are there, you're still looking at a tenfold difference. So what's the calcium sulfate? Tell me about that one. Explain why this is going to be dissolving the most. What does the biggest number mean? Where does this KSP come from? Right? I got some solid, and it's the denominator for a cation and an anion combination. And over here, I got a number like 10 to the negative 38. How do I get 10 to the negative 38 out of this? The numerator was ridiculously tiny, which means iron 3 hydroxide, does that dissolve very much? Basically, no. The answer is no. It doesn't dissolve at all. It's completely insoluble. I mean, I don't even know how you would measure that, honestly. You must have had like a ridiculously large container to get any of it to dissolve. What else? So then tell me about the 10 to the negative 5th. Second? It's the largest number, so that since it's the largest number, that means this numerator must be the largest. So to get an anion, a cation and an anion, that means that the thing must have separated the most. So this is giving me calcium plus 2s and sulfate minus 2s and solid down here, the calcium sulfate. But I have a substantial amount of this because my number is only 10 to the negative 5th as opposed to the other ones. Yeah.
So what is molar solubility?
Molar solubility, it's just the concentration of the soluble portion of the insoluble salt. Sorry. If you added aluminum phosphate and solid silver sulfide to a solution, which ion would be present in the greatest molar concentration? So what do I need to know? I need to know the two KSPs, right? I need to know this KSP, and I need to know this KSP. And there is one other thing to consider, which is what? What? No, well, the insolubility is about the KSP, right? They're not technically insoluble, they just varying degrees of insolubility. The thing that I have to realize, I have to think about a little bit, maybe I don't even have to in this particular case. There is one aluminum ion, one phosphate ion, two silver ions, and one sulfate. So there's a possibility that even though one of them might have a larger KSP, since the other one, when it disassociates, I get double the number of ions, that might play a role. Does that make sense? No? Yeah? So when you're looking at the formulas, think about the ratio of the cations. So I'm asking specifically about which one is there in greatest. So do we have the KSPs for this one? What's the aluminum phosphate? Probably super low. Okay, so a 10 to the negative 21 number. And then what do we got over here? Seriously? 51? 51? Okay, I wasn't expecting that. Cool. So what's the answer to this question? Those guys are going to be equal to each other, right? Does that make sense? No, it doesn't. Why not? What is this? Okay, great. It's a polyatomic ion. It's the anion of what? What section we're talking about? What have we been talking about a lot? Acid, right? So what is this thing? If this thing was an acid, which acid would it be? Be phosphoric acid. It'd be H3PO4. Okay with that? Okay, so if I put phosphates in water, what would the phosphate polyatomic ions start doing? They'd turn into this, right? The answer to this question is aluminum. There isn't any phosphate left. Why? Because it's turning into phosphoric acid. And even if it's a weak acid and some of it disassociates, the PO4 minus 3 is going to grab an H and become HPO4 minus 2. And that's going to grab another H to become dihydrogen phosphate. And then most of them will grab another H to become phosphoric acid. So there won't be any phosphate left when this is finished. Does that make sense? So what's kind of funny about it is even though this is 30 orders of magnitude smaller disassociation, there's going to be more of these two things in the water than there is going to be of this, because there won't be any of that in the water. Dative? I think somebody started to answer this for another question, but what do we got for this one? Okay, so bond formed between two atoms where one atom supplies both electrons. Okay, how about this hydrazine? What's going on with this? Why not? Second? Still not the OH concentration, but at least you got that part right. No. It's not a strong base. So if I take the negative log of it and get my POH, that's not right because it didn't all fully dissociate. Hydrazine is a weak base. So somebody have the hydrazine KB? Okay, so like 1 out of every million of these guys separate out. So I can still use the same formula, right? So it'll be x times x divided by 2.2 equals this 1.7 times 10 to the minus 6th. And then I can say the x is equal to the square root of 2.2 times 2.2 times 1.7 times 10 to the negative 6th. Okay. Mm-hmm. 2.2. Yeah, it's this. So tell me what this is right here. Second? No. The concentration of what? The hydroxide ion concentration. So if you take the negative log of this, you're going to get a number around what? If it was if this wasn't here, what would the POH be? It'd be 3, but that is there, so it's a little bit less than, a little bit more, right? Less, a little bit less. Sorry. What is going on? So I'm gonna get my POH is equal to 2.71. So what's my pH? $11.29. Does that number make sense? Because it's above 7. Okay.
So you actually look at the equation or the chemical formula for that. It's, I don't know off the top of my head. It's like 2 or something.
So here's my hydrazine, and I'm telling you it's a weak base in this section of the notes, or if you looked it up and figured out what it was. So when you've got a weak base, what's got to be happening? Okay. So it's weak, not full dissociation. But if I put weak base into water, what's got to happen? I put a weak base into water, what's got to happen? What happens if I put a weak acid in water? Okay, so if I put a weak base in water, what's going to happen? So what's going to happen to the pH? Okay, so how does that happen? I got, I'll just say a weak base. It's with the water molecule. I need the pH to go up, correct? So what's one of my products got to be? And so then my weak base has an H attached to it. So with any of the weak base problems, that's what happens. It doesn't matter what the weak base is. If I add it as a weak base, it's going to pull an H off of water.
So why don't you have wouldn't you know to use like a 2x?
Anytime you have anything that's weak.
You know what I'm saying? Like when you have the problems they're doing on Tuesday where there's like 2x and there's like raised to the second and you're stuck in that one for a while.
That's totally different. Totally, completely different. That was about KSPs. How come there's no like a 2 here or there? These acids, I'm just going to get one of each thing. Or the bases, I'm going to get one of each. I'm talking about a water molecule that's either going to accept an H plus and become hydronium or lose an H and become hydroxide. So it's only ever going to be 1 and 1. Okay, how about this last one? Okay, so when we look at the properties of acids and bases, okay, any red flags here with this question? What? How about this? The water the acid reacts with the water and in a redox reaction and with the metal. So if I'm reacting, what do metals do? If I'm an elemental metal and I chemically react, what do I always do? What does the left side of the periodic table do with its electrons? It gives them away. So that's technically oxidation. So what is happening to my metal if it's exposed to an acid? It's deteriorating. So does it make sense? Does this question make sense? A basic pH prevents corrosion. Acidic pH causes corrosion.
Well, they just make it look taking some basic.
Because humans have to mess with it. So I wouldn't want to have to open that up at 550 degrees and have to do something with 550 degree Drano. Why not just water? I am trying to make sure it never happens. We're okay with that? So if I make it a pH 10, which is what it's at least in the Navy, if that water inside of that reactor is at a pH 10, do I need to worry about it dropping to pH 6? Even if there's some kind of interjection and I add a little bit of hydrogen to it, so add a little bit of acid, I already have this thing at a pH 10. So I'm going to have to put 3 times as much, or 3 orders of magnitude, 1,000 times more stuff just to get it back to neutral. So it just gives you, it's not a buffer, but it gives you the same effect as a buffer. It's not a buffer because I don't care if the pH goes up, I only care if the pH goes down. And so there's enough in there to make sure that even if some acid does get in there somehow, the pH doesn't drop too much.
So a buffer only weighs out the up or one?
Both.
Okay.
The buffer stops it from happening, either direction. If you walked into a room where there was a bunch of ammonia and you breathed that in before you realized what was going on, that ammonia is a base, and you don't want your pH to go up because you walked into a room with a bunch of ammonia. If you walked into a room with a bunch of acetic acid in the air and took a breath, you don't want your pH to drop. You don't want your blood pH to change at all. So the buffer has to be able to manage both a possible increase and a possible decrease. Mm-hmm.